Good morning, everybody. How are all you guys? Been crazy since we haven't been back to school. Really have missed you. Wanted to know how you did over your spring break. Just how everything is going. Hopefully, you're staying healthy. I'm going to try and do these video notes as best as I can, along with the sheet that I sent for today's Canvas calendar and yesterday's. So I'm going to do all of 3.2.1's notes today. So just be patient. I'll make mistakes just like I do in class, and just give a listen. Hope you're doing well, and like I said, I hope we can talk to each other soon. All right, so let's try this now. Okay. All right, your notes should be up now. What we're talking about in this unit is exponential equations and their inverses. The big thing is you've learned about exponential graphs and functions and everything back from Math 1. You might have touched it in Math 2 a little bit, but now you're going to be touching it again. We've even been dealing with it sometimes this year. But we're going to talk about its inverse, which turns into a logarithm. We're going to start off with the first section, which is explaining how a geometric sequence is actually nothing but a exponential equation, formula, function, all in one. So you'll see with the arrow that we've got the notes, and with the arrow next to the yellow, that's where we are doing the actual, sorry, I had to get up. The actual formula, if you remember, the explicit formula is G sub n equals G sub 1 times r to the n minus 1. And here what I did is I showed you two graphs. One, you'll notice, is y to the 3x, where that one is increasing. I'm glad I can write. Okay, from left to right. That's our exponential growth. Remember, this number right here, this 3 here, is the growth rate, and it's greater than 1, so obviously it's got to be growth. Where in this one here, it's 1/3. That's between 0 and 1, so that's decay. Obviously, then this one is decreasing. Okay, it explains that underneath. What I also decided to do is give you the actual exponential function again, a b to the x, where a is your initial amount, also your y-intercept, your b is your growth rate, and then x is the exponent or the amount of time. Remember, if you don't see a and b, like if they just give you, like in the example up above, it was f of x equals 3 to the x. Well, notice here's your b and here's your x. Well, where the heck is a? A is 1. Okay, so it's really 1 times 3 to the x is what you're looking at for the equation that we did up above. Just so you know that that 1 is then the y-intercept on where it starts. This section also talks about half-life. This is where you drink a Monster and it shows how long it takes for the caffeine to get out of your body. Or carbon dating. Any of you that have done anything either earth science, biology, chemistry, even physics, you should know about what half-life is. It should have been explained to you. It's just something cutting itself in half every certain time cycle. Okay, makes total sense. So if I originally have 20 jelly beans and I'm going to be eating them half each hour, obviously then after the first hour there's 10. Then after the second hour there's 5. And after the third hour there's 2.5, which you can't have, but you know what I'm saying. So we're dealing with half-life. Now, I did not want to be, I did not, I do that all the time. I did not want to be insensitive, but in terms of a realistic approach to this, what I did is I've been following this actually every day online. It gives the growth of the COVID-19 coronavirus in the state of Illinois. And also the deaths. I'm not trying to be morbid or anything with it, but I'm trying to show you that if you're going to be a statistician, or if this case, think about the governor, the mayors, even the president, they've got to use these graphs. It was literally just on Channel 9 about 30 seconds ago, and they were talking about how they're using the exponential spike on the number of cases in the United States. So if this isn't pertinent to what we're doing in mathematics, then I don't know what is. So, you look at the graph and you can see it's a nice histogram. You might remember that from Math 1. And it just talks about each case each day in Illinois. And it is going up exponentially without any question. You could make a table and find the rate of change, see what this, or you could actually use a couple of points between, say, the 22nd of March and the 26th of March and find our rate of change. Remember when we did rate of change, it was kind of like a slope. We can do something like that, and that would show you how much it's increasing. So as you can see by the graph, though, it's a pretty hefty increase. So please don't get sick. So I just wanted to show you the realistic part of that on how that works with the actual section. Okay? Now, I asked you yesterday if you would just try this table. This table actually was pretty easy. If you even so much as just looked at it, you understood what it was meaning. It's talking about Allison and Beth receiving $10 a week for chores for their neighbor. One day, Allison decides to increase her income using her knowledge of exponential growth. She proposes that her payment change to a penny for the first week and then double each week thereafter. So what's happening with Beth is after the first week, she's got $10. And after the second week, she's got 10. And the third week, she's got 10. Okay, she's not adding any money. It's just $10 sitting in an account. Obviously, the slope for this is going to be linear. So her graph better be linear when we put it below. Okay, I mean, it's a constant by 10, but the 10 stays constant, so you're going to see it's literally going to be almost a straight line. Okay? Now, if we look at Allison, if she starts off with putting in a penny, you double that, now you're at 2 cents. And I forgot how to write. There we go. Oops, you know me with this. Okay, and then you double that again, and we've got 4 cents, then 8, 16, 32, 64, $1.28. Even if it's not there, you go down a little bit. 9 is $2.56. 10 is actually at $5.12. And 11, wait, 9, 10, 11 is at $1,024. So $10.24. So in the 11th week, she's now making more money than Beth. Interesting what a penny does. Okay. So if we look at this, how is Allison's income change? How does Allison's income change as the number of weeks increase? Well, as the weeks go up by 1, her amount is multiplied by 2. Should make sense as weeks. I should have said increase, but for now you'll get it by 1. Her amount, her earnings. Yeah, earnings is good. Her earnings doubles. Okay, that should be pretty obvious because what you're doing in this table is you're multiplying everything by 2 to get the next number. Obviously, that is not linear. That's going to be multiplied by 2. That's a common ratio. That's exponential. So one of their actual savings growths is linear and the other one is exponential. This is something we've actually already talked about, so it's not really anything new. It says, does Allison's income represent an arithmetic or geometric? Well, if it's exponential, it's obviously got to be geometric. Explain your reasoning. Well, if she has this sequence and she's doubling it, she's going to have a growth rate, or I'm sorry, an actual common ratio of 2. Okay, so the data has a common ratio of R equals 2. Remember, R is exponential and D is arithmetic. Okay? Then it says, write an equation to represent Allison's income G sub n after n weeks. Well, we've got our G sub n equals G sub 1. Well, if you go back, that was a penny. Times, we doubled it, the rate was 2 to the n minus 1. Okay, that fills in our pattern of G sub n equals G sub 1 times R to the n minus 1. Okay, here's your G sub 1, here's your R. Okay, so it models the formula just like you've learned before. That should be no big deal. Then it says, I jumped around a little bit here. If the pattern would continue, how many weeks would it take Allison to have a greater weekly income than Beth? Well, as I said, in the 9th week it was 256. In the 10th week it was 512. And then in the 11th week it's 1024. So if you look, if we kind of almost just extend the table, how far did it go? Was that 8? So 9 was double $1.28. So 256. 10 was 5. 12. 11 is 1024. 12 is 2048. Look at that. I mean, in 12 weeks, she's actually got double of what Beth has. So how many weeks would it take? It would be after the 11th week. after the 11th week, Allison earns more than Beth. You don't need to get crazy with these. I'm just doing this because you don't see me talking about it in the classroom. Okay? Now the next part, I asked if we could calculate the income that Allison would earn per week in each week given for the 15th week. So here, we're just going to take our formula, G sub n equals G sub 1 times R to the n, which is 15 minus 1. Okay, you do that in your calculator. Let me do that in my calculator off to the side really super quick. Let me call it up really quick. So I hope you've been keeping yourselves busy while you've been on this little hiatus. I hope we're going to be back soon. It doesn't really look too favorable for that, but it would be nice. As I tell you, I'd rather see you guys in person, no question. I can't believe how much I miss my classes, but you guys are awesome anyway, so you know that. Okay, $163.84. So check that out. As Beth keeps getting $10 a week, Allison's up to 163.84. Interesting. In the 20th week, you do the same exact thing. G sub n equals 0.01 times 2 to the 20 minus 1. And that answer is 5,242 and 88 cents. Hope they didn't round it because I didn't do that one. And then the 24th week, G sub n equals the penny still times doubling it again to the 24 minus 1. And that gives us, oh my goodness, $83,886.08. That's insanity. I mean, look at that. After 24 weeks, so 6 months, she's got 83 grand, where the other one is sitting with just $10. It's insane how exponential works so much differently than linear. Now here what I did is I wanted to just show you what these graphs would look like. I thought that that would be something that you might get a little bit out of. I don't know if that makes sense. So Allison, I'll start with first. Allison starts off at amount in dollars, a penny. Then after a week it was 2 cents. 2 weeks was 4 cents. I mean, we have to wait till we get to $1 even here. 4 cents, 8 cents, 16, 32, 64. Yay, now we get to go up to $1.28. 8 weeks was $2.56. 9 weeks was $5.12. The 10th week we found to be $10.24. 10.24. So you'll notice this is definitely discrete and exponential. Beth, she had $10, $10, $10, $10. Oops, I missed the line. Hang on. $10, $10, $10. Probably going, yeah, I am. My glasses are not working, or my eyes aren't working, one of the two. There we go. So you'll see hers is linear, still discrete. Glad I wrote that backward. Now, what happens is I could actually put Beth's graph with her $10. Watch this. 10, 10, 10. Dang it. 10, 10, 10, 10, 10, 10, 10, 10. So you'll see here, if I actually connect them, that right here, you can see that's where Beth is doing better than Allison, because the pink line is above the green one all the way up until look at that 10th week. That's where you can see now that Allison is going to definitely make a lot more, and Beth is just going to continue at the $10. So that's pretty much what this aspect of the unit wanted to show you, this lesson I mean, is the exponential and the linear part of functions on how we can relate them. So those were your overall ideas. That would have basically been Monday. I'm going to sign off for a minute because I need to charge my iPad, and I will come back to you shortly.